Okay, so welcome everybody to lecture number 5 in calculus. So we're going to kick off this morning just by recalling where we were really last week. We'll do a little poll as usual, just to remind ourselves of what we're thinking about, and then we'll proceed to start to discuss some techniques of integration. So really at this point, we're in section 1.4 of the lecture notes, I think, on techniques of integration, and we'll be looking today and tomorrow at the sort of first couple of sections of that. It's really the bulk of the content of our first chapter is in this section, and it's mostly about techniques for calculating antiderivatives. So let's just recall from last week that we had introduced this concept of the indefinite integral of a function. And so the indefinite integral of some function f is basically what they call the general antiderivative of f. So there's a lot of lingo here. But what it means is that the indefinite integral of a function is sort of a general description of all functions that have that thing as their derivative. And of course, two different functions can have the same derivative if their difference is something whose derivative is 0. So if their difference is a constant, so x squared plus 1 and x squared plus 15, for example, have the same derivative because the difference between them is something that doesn't change, that has derivative 0. And so the way it's generally written is that we write indefinite integral of some little f of x is some expression capital Fx. We always insert this plus c, which is the constant of integration. And that's just to kind of capture the idea that functions that a pair of functions have the same derivative exactly if they differ from each other by a constant. So by putting particular values in for that c, that constant c, we sort of get a description of all expressions that have this particular derivative. So probably it's easier to look at a sort of concrete example, a specific example. So the indefinite integral of 2x, for example, is the set of all expressions in x whose derivative with respect to x is 2x, and everything of that type differs from x squared by a constant at most. So x squared plus 1, x squared plus 15, x squared plus pi, x squared itself, all of those things are included in this expression x squared plus c. And we say that that's the indefinite integral of 2x. Okay, so in a sense, like when you kind of practice this a lot, you kind of get it becomes almost a sort of automatic process to write down the plus c after everything. But it's worth bearing in mind what it actually means and why it's there. Okay, it's there because we want to give a sort of full description of all expressions that have that particular derivative. So that's the indefinite integral. And then just to recall the connection between that and the definite integral, which as we know is a more, it's a number, it's the area of some region. And it's something that we defined initially on the basis of sort of applications in which we might want to know it. So to calculate a definite integral, so a definite integral looks the same as an indefinite integral, except that it has these little decorations on the integral sign, the upper and lower limits of integration. And to calculate such a thing, the first step is to find some function, we'll call it capital F, whose derivative is equal to the little f. And then to evaluate that thing at the limits of integration a and b, and to subtract the value at a from the value at b. So for example, if we look at the same thing, the same expression, 2x, but we want to calculate some definite integral of that over some interval, in this case from 2 to 5, then the process is really the same. First step is to write down an antiderivative for 2x. X squared is the most obvious one to write down. You could write down x squared plus 25 if you wanted to, and the answer would turn out to be the same, as we'll see. And then into that, we want to plug in the values of the limits of integration, 5 and 2, and just recall that this notation, x squared with this 5 and 2 written like that beside it, as superscript and subscript on a kind of vertical bar, means this is just shorthand for the expression 5 squared. So the 5 plugged in instead of x minus 2 squared, which obviously is 25 minus 4, so it's 21. Okay, so the answer there is 21. It's a number, obviously. It looks completely different from the answer if we were asked for the indefinite integral. But the connection between them is that basically, if you're taking a definite integral, you're evaluating this antiderivative at the two relevant points and just taking the difference in those two values. So, you know, they're in one sense, they're quite different things. Like one of them's a number, the other one's a family of functions. But on the other hand, the connection between them basically is just that to take a definite integral, we're evaluating essentially the indefinite integral or the antiderivative at the relevant pair of points and taking their difference. So really, I suppose this slide is just to sort of remind ourselves of where we were and to recall the notation as well. And so we're going to pick this up today. And so really, of course, you know, all the work here is in moving from the 2x on the left here to this x squared. And if the problem that you're presented with is something like this one, where you essentially have to find an antiderivative for 2x, well, it's not so bad. We can sort of use our general knowledge of differentiation to write down something whose derivative is 2x. But if it's something worse than that on the left here, you know, maybe we can't do it by just sort of staring at it and identifying an answer. Maybe we can't do it at all. Even after developing lots of techniques, maybe we still can't do it, and that is definitely a realistic possibility. And generally, you know, the problem of writing down a function that has a given antiderivative is a very difficult one. And I don't mean it's just difficult when you're studying it. I mean, it's, you know, in many cases, this question just doesn't have an answer that can be written in terms of the functions that we're used to working with, like polynomials and trigonometric functions and exponential functions and so on. So, you know, it's unlike the process of going from a function to its derivative, this reverse process is one that just doesn't have a collection of rules that apply to every possible example. It's a much more complex business. So we will talk a little bit about that too, but also we'll kind of be sticking to examples where we are able to do something in a lot of cases. Okay, great. So that's sort of where we're at. Does anybody have a question or a comment right now? Okay, if not, then let's just to make sure that we're all on the same page, do a little short poll. So as usual, I have a couple of short questions. There's two here. And again, this is just, you know, to sort of, if it's useful to remind yourself of what we're doing, throw out an answer to these questions. Each of them has one correct answer, I think, out of the 4 options. And I think you should only be able to select one if I've set it up properly. It's an anonymous poll, of course. So maybe we'll just leave it open for a minute and write down your you know, choose your preferred answer in each case, and we'll take it from there. So I'll pause the recording for a minute while everyone is looking at these questions. Okay, great. So we have a very good sample at this stage. If we were going to decide this thing by a referendum, we would have done it by now. So I'll leave it open 5 more seconds. Okay, and turn it off now. Okay, so I'm just going to share the results, and we can just glance at them for a minute. So first question, which of the following is the indefinite integral of cosine x? And there were 4 proposed answers. The one that was most popular was sine of x plus constant, and I agree with all the people who voted for that one. That is the correct answer. So what we have to ask ourselves here, of course, is, you know, what do we have to differentiate to get cosine x? What's an antiderivative for cosine x? And the answer is indeed sine x is an antiderivative for cosine x. And every antiderivative for cosine x has the form sine of x plus some constant, or where obviously the possibility that the constant is negative is included in there. So we don't need to separately say minus. Okay, so yeah, so, you know, that's what we have to ask ourselves. It's very easy, especially when you're put on the spot in an online poll like this, to accidentally differentiate it instead of taking an antiderivative, or to forget whether you should have a negative sign there or not. So, you know, all of the answers I think are plausible. But sine of x, yeah, sine of x is the thing that you have to differentiate to get cosine of x. And that's, I suppose, what we need to be clear on. If we're asked for an indefinite integral of cosine x, we're asked, what do I need to differentiate to get cosine x? And the answer is sine of x. And then the second part of the question, just to look at this, which of the following is the integral from 0 to pi over 2 of cosine x? Again, I think the most popular answer there, which had almost the same vote as in the first one, is again the third one that wasn't deliberate, is 1. So there, what we need to do is we need to take our antiderivative for cosine x, which is sine x. We need to evaluate it at pi over 2 and at 0, subtract the value at 0 from the value of pi over 2, and sure enough, sine of pi over 2 is 1, sine of 0 is 0, and 1 minus 0 is 1. So 1 is the correct answer. But just while we're on the topic of that, maybe I'll just make a small comment about it, because I think it is kind of a curious and remarkable fact that integral is actually equal to 1. So let me stop sharing the results of the poll. If anyone has a question about that, feel free to ask now or to ask me later. Let's stop for a second in case anyone does. Okay, so stop sharing the results of the poll. Let's close that. And maybe let me just comment for a second about the second part of it. So what we said there was that the integral from 0 to pi over 2 of cosine x is 1, and of course we can confirm that by going through the motions of the steps. this should be sine of x, which is an antiderivative for cosine x, evaluated from pi over 2 to 0. So it should be sine of pi over 2 minus sine of 0, which indeed is equal to 1 minus 0, which is equal to 1. So we can sort of confirm that if we believe the process, that's the answer it gives us. But what it actually means, I think, is sort of interesting. That, if you look at the graph of cosine x from 0 to pi over 2, cosine of 0 is 1. Okay, it's the x coordinate of the point 1, 0. And the cosine function decreases from 0. It hits the value 0 at pi over 2. And then it decreases again to minus 1 at pi, and it turns around. So that's what it looks like. So this is the graph y equals cosine x. And so I guess the remark that I'd make is that we're talking about this area, which is the area of this region, which is bounded by this quite complicated curve, y equals cosine x at the top. And we're saying that the area of this region is 1, which is interesting in my opinion. The number pi over 2 here, which is the right-hand endpoint of the region, is an irrational number. It's pi over 2. It's not something that's very easy to sort of get at. It has a non-repeating, non-terminating decimal expansion. And the value of the cosine function at, for example, the number 1, which is somewhere here, is some irrational number as well. But yet the area enclosed by that cosine graph between 0 and pi over 2 is actually the rational number 1. It's a very nice thing. So I don't think there's any sort of really quick, easy way to see, without having the techniques of the principles of calculus at your disposal, that the area of that region is 1. And one of the things that will be a recurring theme in this course is sort of connections between rational and irrational numbers. And here we have the cosine function. Okay, obviously it has both rational and irrational values, but for example, the right-hand endpoint here of this interval is a very irrational number, pi over 2, but the area enclosed under the graph is just the number 1, which is kind of one of the nicest numbers you could ever meet in terms of dealing with. So that's just a remark. Sometimes you get these sort of connections, especially when you're dealing with circles, obviously between pi and various nice rational numbers. But yeah, so the fact that that area is 1 is quite a cute thing. And of course, if you were to integrate the cosine function from, let's say, minus pi over 2 to pi over 2, minus pi over 2 is over here. Okay, this is a terrible picture. But that, again, the sort of left-hand, the area of the sort of left-hand part of that sort of hump that isn't shaded is also 1. So the integral from minus pi over 2 to plus pi over 2 of the cosine function would be 2. So that's just a few remarks. I think personally for me, I suppose the reason I raise these things is because when you're doing these examples, it becomes a fairly mechanical process, but it can be nice to kind of remind ourselves of what is it that we're actually saying here. We're saying something about a region that's enclosed by the cosine graph, and that's quite an important thing. So sometimes it's nice to recall what it is that we're doing. Okay, the plan for the next couple of lectures, today and tomorrow, and actually also next week, is to basically look at some different techniques for finding antiderivatives. And it's split up into a few sections, as you've probably already seen by looking at the lecture notes. So essentially, in this section, we're going to have basically 3 different techniques of integration. One of them is so-called substitution technique, which we'll start looking at today. We'll continue looking at that in tomorrow's meeting. The other 2 sort of specific techniques of integration that we're going to look at next week are so-called integration by parts and something called partial fraction expansions, which works for a specific category of examples. And there are endless techniques of integration, as you can find out by looking at a calculus book. We're only really going to look at 3 of the major ones, and we basically have sort of a lecture devoted to each of them. Before we launch into the 3 sort of specific techniques, we're going to start today by just looking at a few classes of examples that don't kind of quite fall into any of the techniques, but that can be dealt with sort of directly. So the first few examples today are kind of what I'm calling things that you can deal with by direct methods. After that, we'll move on and talk about some examples that are amenable to these particular techniques. But I should emphasize that the techniques we're going to talk about are not exhaustive at all. There are loads and loads of examples that none of them apply to. So you can form the impression when you're practicing with examples that if you only know the right trick, you can integrate anything. That's not really true. It's more true that we choose examples that are amenable to the techniques that we're trying to learn about. So bear that in mind also as we proceed. Okay. First category of functions that anybody might like to be able to deal with quite often are polynomial functions and sort of powers of x. And certainly we know that they behave quite well with regard to differentiation and also with regard to integration. So this one is listed here as an example, but really it's one that we should have in our sort of toolkit in our general repertoire of things that we know how to integrate. So basically, if you want to integrate a power of x, how do you do it? That's our question here. And of course, we know that if you want to differentiate a power of x, how we do that. I should mention also that most calculus textbooks and also the formulas and tables booklet that's used for the Leaving-Cert, if you happen to have a copy of it in your possession, have tables of sort of standard derivatives and integrals, which are very handy for a reference. So, you know, I'm not really suggesting that you should memorize these things, although you probably find that you do that anyway, kind of organically. And the relevant pages in the formulas and tables booklet of tables of derivatives and antiderivatives are quite handy to recall these things, you know, for derivatives of trigonometric functions and polynomials and so on. Okay, so suppose you want to determine the indefinite integral of some power of x. Well, okay, there we have to ask ourselves, what do I need to differentiate to get x to the n for some n? So n maybe is not necessarily an integer. It could be anything. So what do I need to differentiate to get x to the n? So think about that for a second in your own mind. And of course, I mean, we know that when we differentiate a power, the power goes down by 1. And okay, you pick up a constant multiple, but you know, if I want to get something like x to the n, I should differentiate something like x to the n plus 1. That's the first observation. So we know that if we differentiate a power of x, we get x to the exponent 1 less multiplied by the original exponent. So we need to sort of reverse that process. So in order to get x to the n, I should basically differentiate x to the n plus 1, more or less. If I do that, I pick up a multiple of n plus 1 that I don't want, so I should compensate for that by multiplying by the constant multiple 1 over n plus 1. And if you differentiate 1 over n plus 1 times x to the n plus 1, you get, well, the constant multiple 1 over n plus 1 just sort of survives. So you get 1 over n plus 1 times n plus 1 x to the n, which is the power 1 less than n plus 1. So you just get x to the n. Okay, so essentially the answer to what's the indefinite integral of x to the power n is this gadget, plus the constant of integration, of course. So to find an antiderivative for x to the n, we have to increase the index from n to n plus 1 and basically divide by the new index, 1 over n plus 1. Okay, so a general antiderivative for x to the n is x to the n plus 1 over n plus 1 plus constant. And when you do, you know, when you get into the habit of doing these things, I think the sort of thought process that goes through most people's minds is, let's say if you want to integrate x to the 5, say, okay, well, I need to increase the power by 1 to x to the 6, and I need to divide by the new power and add my constant of integration. And so, you know, the sort of mantra is increase the power by 1, divide by the new power. If it doesn't just work for integers. If you want to integrate square root of x, x to the 1/2 works for that too. We need to increase the power by 1 to 3 over 2, divide by the new power 3 over 2, which means multiply by 2/3, and don't forget your constant of integration. So that's sort of how it goes. Okay, and of course, one nice thing about this, which is a good sort of mental habit to get into as well, I think, is that generally you can sort of quickly check your answer. You know, you can sort of confirm by differentiating this expression that its derivative is indeed x to the 1/2. You see, okay, yeah, well, the 2/3 and the 3 over 2 cancel, and you're left with x to the 1/2. Constant of integration gives you 0 when you differentiate it. So that's a kind of general formula, I suppose, for integrating powers of x. And it works perfectly well as long as the denominator that you introduce here at this step is not 0. And of course, we should all be at high alert all the time for any possibility that we could be dividing by 0, because that means that we are making no sense and we need to reevaluate what we're doing. So as long as the number n is not equal to -1, which means that this denominator n plus 1 is not 0, this is perfectly fine, perfectly reliable, and works really well. And of course, the information in this slide enables us to integrate anything that's like a sum of powers of x multiplied by constants, because, you know, if you want to integrate x to the 1/2 plus x squared, something like that, because the integral and derivative operators are linear, all you have to do is deal with each part separately. So, you know, integrating the x to the 1/2 would give us x to the 3 over 2 divided by 3 over 2, so multiplied by 1/3, by 2/3, plus the x squared part can be dealt with separately. That gives us x cubed over 3 plus our ever-present constant of integration when we're dealing with indefinite integrals. So, you know, anything like that, then we can basically deal with. Okay. Okay, that's one sort of really important class of things that's dealt with in this slide, and of course it covers a huge multitude of functions, powers of x, and of course if you had 3x squared instead of just x squared, here you just add in an extra factor of 3. So okay, that covers all powers of x, with the exception of x to the power minus 1. One other thing that's covered there, which I should probably give a special mention to because it's easy to forget that this is actually included there, is so note that this example includes the only thing that it doesn't include is 0. So if you have to take an indefinite integral of a constant function like 1, that's actually the integral of x to the 0 dx. So it's just increase the power by 1 from 0 to 1, divided by the new power, that's 1. So it's just x plus c. Of course, we can see that anyway, that x is something whose derivative is 1, but we can even incorporate it into that formula. That's just an observation. If, for example, you wanted to integrate 5, what has derivative 5? What 5x does? This is 5x plus c. If you wanted to integrate something like 3x plus 1, you'd integrate 3x first. That means we've got a 3, increase the power on the x by 1 from 1 to 2, divide by the new power, and we've got a plus x from the plus 1. So it's 3 over 2x squared plus x plus c. So basically, by applying the content of that last slide, we can deal with any sort of expressions like this, where we've got a sum of powers of x, maybe each multiplied by a different constant. We can handle all those sort of things. And remember that sort of constants themselves, like 1, are kind of included in that framework, even though we can include them separately in our minds if we want to. Okay, so that's the first sort of big class of examples. The thing that it doesn't cover is 1 over x, x to the power minus 1. So we'll deal with that next. Does anyone have a question about any of that? If you do, please don't be shy about putting a question in the chat or about turning on your microphone and asking one. I don't want to be going either too fast or too slow. Okay, great. Okay, so the power of x, I suppose, and the reason for including this next is that we've kind of covered now all powers of x except for x to the power minus 1. So this is sort of, kind of should have fitted into the framework of the last slide, but didn't because of this problem of having to introduce a denominator, which in that case would be 0. So x to the power minus 1, of course, is 1 over x. And now we have to ask ourselves, well, there's a hole here in our theory for powers of x at this point. So how are we going to deal with that? Okay, well, here we have to kind of remind ourselves of derivatives relating to 1 over x. So just to recall, I'm sure this is something that you studied in semester 1 with Graham, that we have this function, the log function, which is quite a sort of mysterious, but also quite an important function in calculus, which is related, of course, to the exponential function. And one thing that we know about the natural log function is that its derivative is 1 over x. And I suppose, 1 over x is a very simple, nice thing that we all sort of encounter, at some point in our primary education. We learn about fractions and about 1 over x, but the log of x is quite a sophisticated thing that we only learn about, really, if we study mathematics at 3rd level. So, but these two functions, 1 over x and log x, have this very kind of close, important connection. Okay, so why are we suddenly talking about log x? Well, because we have to somehow find something whose derivative is 1 over x, and that's log x. So just to recall something that you, I'm sure, studied previously, if we just take a positive value of x, okay, the reason for taking x to be positive here is that the log function is defined only for positive values of x. Okay, and the reason for that is only a number that's the exponential of something can have a log. And the values of the exponential function, e to the power any real number, are all positive. So only positive numbers occur as exponentials, which means that only positive numbers have logs, because the statement that y is equal to the log of x means exactly that if we take e to the power y, we get x. Okay, and that of course means that x must be positive, because no matter what y is, no matter what real number y is, it's e to the power y will always be positive. Okay. So we've now introduced an exponential function and a log function for no apparent reason, but it's to get at something whose derivative is 1 over x, of course. So, okay, so e to the y is x. If we differentiate both sides of this equation, with respect to x. So remember, e to the y is equal to x. Y is a function of x. So to differentiate e to the y with respect to x, we need to apply the chain rule, bearing in mind that y is a function of x. And the chain rule would say, well, first of all, we should differentiate e to the y with respect to y and get e to the y. And then we should multiply that by the derivative of y with respect to x. Okay, which at present we're pretending that we don't know. So we're just going to write it as dy dx. And the right-hand side of our equation is just x. And when we differentiate that with respect to x, we get 1. Okay, so applying the sort of implicit differentiation formula to the equation e to the y equals x, where y is defined to be the log of x, we get that e to the y dy dx is 1, and rearranging that, we get that dy dx is 1 over e to the y, which is 1 over x. Okay, so the point of this line is just to remind ourselves of the statement that the derivative of the log function is 1 over x. And again, if you want to sort of think about that, remember that the graph of the log function looks like this. The log of 1 is 0. And as if we have a number that's greater than 1, its log is positive. It's a positive power of e. The log function sort of tapers off and grows more slowly as we travel out. And it's negative for values of x that are less than 1. And it's not defined at all for negative values of x because they can't be exponentials of anything. So this is the graph y equals log x. And what we're saying when we say that the derivative of that graph is 1 over x is basically that the slope of the tangent line to this graph kind of looks like 1 over x as we travel along. So it's 1 when x equals 1. It's higher than that. It's a steep slope when x is less than 1. And it sort of tapers off eventually as 1 over x does to 0. Okay, so just, I suppose, I don't know if that's need some of those pink smudges. Okay, so the derivative of log x is 1 over x, and that tells us at least that for x positive, that the antiderivative of 1 over x should be log x. Okay, so that's fine. And that applies as long as log x is defined, which means that x is positive. So one kind of small observation there is that that's all well and good, and perfectly all right, except for the small minor kind of complexity that log of x is only defined if x is positive. But 1 over x, of course, is defined as long as x is not equal to 0. So we'd probably like to have an expression for the indefinite integral of 1 over x that would apply for all values of x on which 1 over x is defined. So something that you can observe, of course, and I'll leave you to check the details, they're also in the lecture notes, is that if x is negative, then we can identify by this exactly the same process as at the top of this slide, that the derivative in that case of the log of minus x, which is defined if x is negative, is 1 over x. So in general, we can say that the antiderivative of 1 over x is log of minus x if x is negative, and it's log of x if x is positive. So in general, it's log of the absolute value of x. This applies as long as x is not equal to 0. The fact that x can't be 0 here is not really a problem at all, because 1 over x itself is not defined when x is 0. Okay, so the general antiderivative for 1 over x is log of the absolute value of x. So if x is negative, we can observe by the same argument, then the derivative of log of minus x, which is a well-defined thing because minus x is positive if x is negative, is also equal to 1 over x. So the antiderivative of 1 over x there is log of minus x, which is also log of the absolute value of x. So writing the absolute value of x here is just sort of, it's a little technical tool for writing the expression in a uniform way that applies both for positive and negative values of x. So there is sort of a discontinuity there at x equals 0, but it's not an issue because there's a discontinuity in the function 1 over x itself as well when x is equal to 0. Okay, so this is one to bear in mind. Again, like it's in the tables of integrals in the formula and booklet, in the formulas and the formulas booklet, so you don't need to memorize it, but I suppose it's definitely worth having in our minds the fact that the indefinite integral of 1 over x, the antiderivative of 1 over x in general, is log of the absolute value of x. And in general, I suppose, if you want what you write to be sort of true in the broadest possible context, you sort of do need the absolute value here. Otherwise, what you're saying is only true for the positive values of x. Okay, so that kind of completes the story, I guess, of integrals of powers of x, which is sort of the point here. By adding the story for 1 over x, which is the exceptional one, we kind of have a full picture now of antiderivatives for expressions which are powers of x. Does anybody have a comment or a question about that? I guess if you're kind of not immediately familiar with it, the thing I'd sort of suggest reminding yourself about, if necessary, is just the derivative of the log function from the notes in semester 1. But that deals with all the powers of x. And then there's just one final example, I think, in this section before we move on to more specific techniques. And this is just a definite integral, actually very similar to the one that we looked at earlier in the little poll. So here we've got a couple of trigonometric functions, and I guess again, you know, derivatives and antiderivatives of trigonometric functions we sort of generally know about. The derivative of sine x is cosine x. The derivative of cosine x is minus sine x. So we can reverse those expressions to write down antiderivatives for cosine and sine. These are worth having in your mind and easily accessible in your sort of consciousness. But if they're not right now, just check them in the tables and formulas booklet or wherever you have a useful table. There are tables of these things also in the lecture notes, but not as detailed as the ones in the formula and tables booklet. So yeah, so if you want to integrate sine of x plus cosine x from 0 to pi, let's say, this is a definite integral. So I guess one of the things I'd highlight here is when you're dealing with a definite integral, you don't really need to worry about the constant of integration, because you know you're just going to be evaluating your antiderivative at 2 specific points, and if you had a constant of integration there other than 0, it would just cancel in the calculation. So we need to write down any antiderivative of sine x plus cosine x. You don't need to bother with the constant of integration. If you do put something in there instead of 0, it doesn't matter, it'll cancel in the final calculation. So what do we need to differentiate to get sine of x? Minus cosine x, because if we differentiate cosine x, we get minus sine x. What do we need to differentiate to get cosine x? Sine x. Okay, so our antiderivative for sine x plus cosine x is minus cosine x plus sine x. We need to evaluate that at pi and at 0. So we get minus cosine of pi plus sine of pi. That's the evaluation at pi. From that, we need to subtract the evaluation at 0, which is minus cosine 0 plus sine of 0. And personally, I find it useful to kind of write down the step in detail just to make sure that I don't get the signs wrong, even though you could probably do it in your head, just to kind of make a careful note of what it is you need to calculate, and then write down all the values. Cosine of pi is minus 1, sine of pi is 0, cosine of 0 is 1, sine of 0 is 0, so we do all that cancellation and we get 2. And just a remark here as well, in case you're wondering about, you know, how do I know off the top of my head that cosine of pi is minus 1, just remember the meaning of the cosine and sine functions. And I think when we studied trigonometry in school, we tend to have a tendency to think about sines and cosines in terms of triangles. But that is a tendency, if you have it, that I'd advise you to try to lose if you can, because it's not really the complete definition of the sine and cosine functions. So the definition of cosine of pi is, pi is a number, first of all, it's not an angle. Here's the point 1, 0, and there's the unit circle. So the definition of cosine of pi is that it's the x-coordinate of the point that you get if you start at the point 1, 0 and travel in an anti-clockwise direction around the unit circle for a distance of pi. The circumference of the unit circle is 2 pi. So a distance of pi takes us halfway around. And then at that point, we reach the point whose coordinates are minus 1 and 0. And that's the cosine of pi and the sine of pi. So, you know, basically you can think about trigonometric functions. They're functions of real variables. They're not really functions of angles or anything like that. And so the cosine of a number is the x-coordinate of the point that you reach by starting at 1, 0 and traveling anti-clockwise around the unit circle for a distance equal to that number. So if it's 2 pi, you're back to where you started and it's 1. If it's pi over 2, you're here and the x-coordinate is 0. If it's 3 pi over 2, you're here and the x-coordinate is 0 again, and so on. So that's the meaning of cosine and sine. So the cosine function keeps track of the x-coordinate, and the sine function keeps track of the y-coordinate. So the sine of 1, for example, would be the y-coordinate of the point you would reach by starting at 1, 0 and traveling a distance of 1. So 1 is less than pi over 2, so you'd be here somewhere. And the y-coordinate of that point is the sine of 1, which is not an easy thing to calculate, because the coordinates of that thing are not particularly nice numbers. But that's the meaning of it. It's the y-coordinate of the point that you reach after traveling a distance 1 around the circumference of the unit circle in an anti-clockwise direction, starting at 1, 0. Okay, so I think thinking about that when you have a bit of time to just sort of reflect on it is a really useful thing, and it means you'll be able to just sort of read off the values of sine and cosine of things like pi over 2, 25 pi over 2, pi minus pi, and so on, really quite easily. Okay, so that's just a reminder, I guess, of the meaning of the basic trigonometric functions. Anyone have a comment or a question? Okay, in that case, so that's kind of that's the end of the sort of introductory part of section 1.4, which is basically integrals that we can deal with without any special techniques, I suppose, is how I'd sort of describe it. There are 3 sections coming up in this section 1.4. They're numbered in the lecture notes 1.4.1, 2, and 3. And they're basically sort of 3 specific techniques of integration for dealing with specific types of problems, which are all, I think, can be, I suppose my advice to you with each of the 3 of them is just practice, practice, practice with lots of examples. This is something that we can, it's a technical facility that we can learn by working with examples. Which I think in mathematics, there are some things that you can learn by working out examples, and some things that you have to learn by sort of contemplating concepts. And these things are in the working out examples category. Okay, so I'd say work with the examples here in the lecture notes, in the homework sets, and also pick up a calculus book, or have a look at one online and practice examples there and make sure that you're confident with these techniques. Okay, this is the preview really for tomorrow. What are we going to be talking about in the substitution technique? So as we know, the rules of differentiation, basically we have the product rule and the chain rule. I mean, we have the quotient rule as well, but personally, I think the quotient rule is a version of the product rule. It's not really a separate rule by itself. So we have the product rule and the chain rule for going from a function to its derivative. And if we want to be able to go from a function to an antiderivative, we need to have some kind of ways of reversing these rules, which is not easy in general, but we need some ways to try to do it. And the substitution technique is a way of reversing the chain rule of differentiation. That's how I think of it. Unfortunately, it's not a rule that you can write down like the chain rule. It's kind of a strategy that you can try that works some of the time. So there isn't it's not a theorem like the chain rule that you can say, well, here's a statement of it, now I have to apply it. It's kind of it's a technique, a method that you can try to apply to examples with the hope of success. So just to introduce it, here's an observation. Suppose you wanted to differentiate something like sine of x squared. I mean, the rules of differentiation tell us how to do that. We should say, well, looking at this thing, it's the sine of something. So I should differentiate it and get the cosine of something, and then I should look at what the something is, and I differentiate that and multiply by the derivative of that. So to differentiate sine of x squared, I get cosine of x squared multiplied by the derivative of x squared, which is 2x, so I get 2x cosine x squared. That's pretty much how we'd apply the chain rule to that problem. Maybe you wouldn't apply quite the same form of words. I'm kind of sharing the thoughts that would go through my head, which might not be representative, but anyway, that's what I would do. So another way to say that, of course, is in the language of antiderivatives and indefinite integrals, is that the indefinite integral of 2x cosine x squared is sine of x squared plus constant. Okay, and this hopefully sort of highlights where the trickiness is, because if somebody hands you sine x squared and asks you to differentiate it, you can sort of immediately see, okay, this is a case for the chain rule. It's the sine of something, the derivative is the cosine of that thing multiplied by 2x. But if somebody hands you this version and says, find an antiderivative of 2x cosine x squared, well, you have to kind of try to figure out, well, where did this come from? Who differentiated, what did the person differentiate to get this? And it's harder to kind of put the pieces back together in reverse. So in this section, what we're going to try to do is consider how one would go about reversing the differentiation process to get from 2x cosine x squared back to sine of x squared. Okay, that's much harder than the opposite direction. So here's a quick example that we'll pick up here tomorrow. I'll have a very quick look at it now, just to give it, and we'll start here tomorrow with this example. So supposing you are asked to determine the indefinite integral of this thing, 2x multiplied by the square root of x squared plus 1. Okay, so it's not, on the one hand, it looks kind of not too bad because we know how to deal with powers of x. But what we have in the second factor here is not a power of x, it's a power of x squared plus 1. So we can't just kind of do this like we would do a polynomial. That's the first observation. Second observation, and this is the thing that I suppose I'd advise you to be on the lookout for when you're dealing with examples. We can observe that here in the thing that we're trying to integrate, which is the integrand, we have x squared plus 1, and we also have a 2x. Okay, the x squared plus 1 has a square root sign around it, but temporarily disregard that and notice that we have an x squared plus 1 and a 2x. And also notice that 2x is the derivative of x squared plus 1. because that's something that might give us a sort of foothold to hang on to if we want to find an antiderivative. And the reason for that is the following. So this is the so-called substitution technique. If we introduce the notation u and define u to be x squared plus 1, notice that the derivative du dx is 2x, and do this thing that you're not supposed to do, which is imagine that the du dx was an ordinary fraction, and rewrite that as du equals 2x dx. And then using that, rewrite the whole integration problem in terms of u. So the square root of x squared plus 1 part is the square root of u. The 2x dx part is du. And then we see that what we have is an integral of the square root of u over u rather than over x. It's a du rather than a dx. Integrate that as a function of u. That means just increase the power here by 1 and divide by the new power. We get 2/3 u to the 3 over 2 plus c. And then rewrite everything in terms of x, and you get an answer that you can check works. Okay, so this is a sort of preview of how the substitution technique works. If you didn't follow that sort of quick preview, don't worry at all. I don't really expect that you will. We're going to, but it's just sort of a glance at it for the moment. And we'll pick up there tomorrow and talk in more detail about how to implement this technique. And I'll try to explain a little bit as well about why it works. But essentially what it does is sort of reverse the machinery that's applied in the chain rule. Okay, I'm going to stop the recording there and things open for questions for a couple of minutes if anybody has one. And thanks to everybody who's joining us for the recording, which is stopping.